very welcome everyone to our first session of InnoCrypt 2020. The first talk is about encrypted key value stores and by Achita Agrawal and Seni Kamara. And Achita is going to give a short introduction and then we can ask questions.
Yeah, thank you, Chris. Am I audible? I'm not sure. Okay, awesome. Yeah, hi everyone. As Chris said, my name is Archita Agarwal and I'm a student at Brown University. And today I'll give a brief summary of my work on encrypted key value stores. Oh, my slides are stuck for some reason. Oh, okay. So key value stores are one of the most basic building blocks of many distributed systems. So for example, Amazon's Cart, Google Drive, Dropbox all make use of distributed key value stores to store our data such as photos, emails, messages, our personal files that we upload, and so on. And we see so many data breaches that happen every year, which steal our sensitive data, right? So since these key value stores are such a basic building block of these storage systems, so if we can get encryption into them, we can then build all sorts of privacy preserving storage systems on top of them and hopefully prevent some of these data breaches, if not all. So question is, what are these key value stores? These key value stores are distributed and decentralized systems that are used to store and retrieve data to and from servers that can be spread all over the world, right? So these are servers, they can be anywhere in the world, and we want to store data in them and retrieve from them. So to support such data storage and retrieval, key value stores support two operations: get input, like dictionaries, and the main sort of key property of these key value stores is that they support replication for fault tolerance. So instead of storing your one key value pair on just one single node, they will be storing it on multiple nodes. So if one node goes down, they can still fetch your data from these other nodes. And then to keep these sort of replicas in a consistent state, these KVSs or key value stores, they employ some sort of synchronization mechanism. So in distributed systems literature, actually there is a whole spectrum of consistency notions. Some are weak and some are strong. So depending on sort of the use case, a key value store can sort of provide you with one of these consistency. So now for the rest of my introduction, instead of calling them key value pairs, I'm going to use the term label value pairs because key I'll be reserving for cryptographic keys. Okay. So I don't have time to sort of give you the construction, but we use provable security paradigm to analyze the security of the construction. So we first define the syntax, then the security definition, and then show that the construction is sort of secure under that definition. And in our work, we consider two different settings, the single user setting and the multi-user setting. In the single user setting, clients or the users, they do not share their data with each other. Okay, whereas in the multi-user setting, they do share data with each other. So what can happen is that there are two entities, two users, which are operating on the same label value pair at the same time. So there are concurrent operations, but in single user setting, that's not what's going to happen. So we show that in the multi-user setting, the EKVS construction or the encrypted key value construction is L secure with high probability. And where L sort of stands for the leakage, and it is equal to when do the clients repeat their operations on the same label. So it's sort of a repetition pattern that is leaked. So you do not leak the label itself, but just when do the clients query for the same label again, right? So it's a repetition pattern. And the key thing is that this sort of setting reveals the operation equality of all the labels that are stored, irrespective of whether a label value pair is stored on a corrupted node or on a good node. So it doesn't care. Whereas in single user setting, we can show that this leakage can be improved and the adversary can only learns about the operation equality or the repetition pattern of just the subset of labels. And this subset, which subset is sort of determined by the properties of the underlying KVS. And in particular, we isolate 3 properties of key value stores, and we show that these 3 properties, they affect the security of encrypted key value store. So we call the first property the balance, the second non-committing allocations, and third the consistency. I'm not going to define these. So we show that if your key value stores, plain text key value stores, satisfies these 2 properties, and satisfies read or write consistency, then it's possible to improve the leakage in the single user setting. So precisely you can show that you just then leak the repetition pattern of the pairs, of the label value pairs, which are stored on the corrupted nodes. Okay. And this was sort of particularly exciting for me because we had not seen these kinds of works before where you explore sort of the fundamental connections between cryptography and the distributed systems properties like consistency or balance or non-committing allocations. So for example, it'll be interesting to explore this sort of link more in detail, as in what is the connection between the leakage and the consistency guarantees of distributed systems. So for example, do stronger notions of consistency give you better privacy? So because if you see in the single user setting, by assuming read or write consistency and some other properties, you could improve the leakage. So is it true in general? And if yes, can you then improve the security in multi-user setting as well by assuming some sort of consistency property? And if not, then can you show the lower bound on the leakage that you have to leak sort of this much in the multi-user setting? Yeah, that's all, and thank you.
Thank you, Ajita, for the nice introduction. Maybe you can start with a quick question of my own. So what is your intuition? Does do stronger consistency requirements give you better privacy, or in general, or you don't know?
I don't think so, because there were examples that we explored whereby even by assuming the strongest notion of consistency, we were not able to bring down the leakage. And the reason was that as you go towards a stronger consistency, which means that for every operation, you would have to touch multiple nodes in the network just to make them just to bring them in a more consistent state, just to synchronize them better. And now, because you're touching more nodes, you're sort of leaking more.
Right.
So maybe not, yeah.
Yeah.
So I would go more towards lower bound than trying to improve it.
Thanks. All right, then if there are no further questions, then maybe we can move to the next presentation.
Sure. Yeah, I can take questions on chat as well if someone has any. Thank you.
So,
I guess, can you hear me?
Yeah.
And can you see my full screen thing?
Yeah, all good.
Okay, great.
So,
should I start or should I wait for the?
Say that again.
Do we start immediately or do we wait for synchronizing talks or something?
Yeah, we can start. I think it's about time now anyway. So our next talk is by Vasilis Tsikas with his co-authors Leonard Kleinrock and Raphael Ostarovsky on proof of reputation blockchain with Nakamoto fallback. So Vasilis, hand over to you.
Thank you, James. So I'm going to discuss blockchains, and let me briefly start with blockchain-based ledgers. people probably know what a blockchain-based ledger is, but when we are trying to decentralize or emulate such a blockchain ledger, there are two main questions that we are asking, and those are who can propose the next block and how can we agree on the ledger state. And those two questions are the ones that kind of we see the differentiation between different technologies. So the most common way nowadays that have been used for answering who can propose the next block are the so-called proof of work way, which says that the proposer of the next block has chances to win a lottery and propose the next block by proportional to his hashing power. The proof of stake says that the proposer of the next block is chosen according to the stake that he owns. And in this work, we propose a different resource, namely reputation. The idea is that the proposer has chances to win proportional to his reputation. So now, how can we agree on the blockchain ledger state? Well, the answer here is kind of uniform in all these technologies. Is like but the way to do it is we try to get an implicit consensus mechanism based on quality of those assumptions. For example, based on the majority of work being in honest hands, majority of stake being in honest hands, and in our case, based on accuracy and quality of the reputation. I'm going to say a few more things. Okay, so how can we use reputation as a resource? We introduce what we call a reputation system. This is associating to each party in the system a number from 0 to 1, which corresponds to his reputation, namely the probability of this party behaving honestly in the system. So more reputable parties have higher chances of being honest. And in this work, we're going to focus on uncorrelated reputation. So these probabilities are independent. So this kind of, you can think of them as ranks in a standard like online ranking system, like Yale, TripAdvisor, and so on. Now, how can we use such a reputation system to devise a blockchain? Well, what we can do with it is if anyone gives you a set, then you can decide what are the probabilities of this set, say, having an honest majority or having above some threshold. And even better, you can actually use the reputation to choose a set with this probability, with this property, whenever possible. So that's what we're going to do here. And I'm going to give you a very, very brief overview of the way the protocol works. So what we do is we proceed in rounds. In each round, there is a committee of endorsers, very small, a sublinear committee of endorsers chosen, and then a subcommittee of proposers. And what happens is that the proposers have their inputs, which are, say, the transactions that they've heard, and they want to propagate them. So what they do is they broadcast them by a Byzantine broadcast protocol so that everyone hears the same thing. And then all the endorsers sign the set that they've heard, and they circulate it amongst themselves. And whoever hears such a set with a majority support propagates the set and the support to the rest of the network, which then accepts the message if there is majority support or doesn't accept it otherwise. So the protocol is in general very simple. And then we advance the next round, again, another committee and so on and so forth. So what is the challenge in such a protocol? The challenge is to select a sublinear, a small committee which has honest majority. Now, is that always possible? The answer is no, and it's very easy to verify. So if all the parties have very low reputation, say under 1/2, then there are very little chances that they're going to get honest majority committees, no matter how many parties you choose. Now, the good news is that there is work by Sarov, Lindell, and Zarosim that shows that there is a way, for all reputation systems which allow such a selection, there is a way to have a selection with honest majority. And it's not that hard to guess. What you do is you just order the parties according to the reputation, and you choose the most reputable one, what you would expect. So this does kind of give you a way of selecting such a committee. And just as a note, I'm going to be calling these reputation systems feasible reputation systems, the ones that allow us to select honest majority committees. But the problem of this selection method is that it doesn't have a fairness guarantee. So always the highest, the parties with the highest reputation are selected. So anyone who is not in this set doesn't have any chance of being selected or incentive to be in the system. So what we do, we introduce a tiered version where we separate the parties in different tiers, and a definition of reputation fairness, which requires that the probability of a party being in the selected set corresponds to his reputation. So a party from the high set, from T1, say, is twice as likely to be selected than T2. When parties are from the same tier, they have the same probability, and then the representation of parties from different tiers is proportional to the reputation, twice the number of the lower tier. And these two can be actually played with according, depending on the reputation number, the number of reputation tiers. All right. So the nice thing is that this third property, if you have, let's say, more than 4 reputation tiers, will also give you honest majority, because you have a kind of exponential reduction in the number of parties you're selecting from lower tiers. If you have a lottery that satisfies the selection, then you get honest majority. And we do give in the paper such a lottery. What are the benefits from using such a reputation system? We're getting a blockchain with a good finality, like the iterated BFT protocols. And the other thing is that a reputation gives us some information on the adversary. It's an assumption about what the adversary would do if you think about it as a cryptographer. So I know the probability by which a party is going to get corrupted. So there's no need to discuss adaptive corruption, right? The party is going to get corrupted with that probability. Maybe that probability changes. We can discuss dynamic reputations, but not adaptive corruptions per se. And this allows to have like less communicated messages, and this lowers the communication overhead of the protocol. But you might be thinking that reputation is subjective. How do I know the reputation of a party? How do I guess this probability? Of course, it's a manipulatable quantity. Parties might misbehave to increase the reputation, and then might behave honestly to increase the reputation and then misbehave. So to address this, what we do is we devise a hybrid design where the proof of reputation blockchain is used as a primary blockchain. All transactions occur there. But then, in parallel, independently and asynchronously to that blockchain, we are actually running a Nakamoto-style blockchain, like a proof of stake or proof of work blockchain as a fallback, where we just put digests and resolve complaints. And what we prove is that if the reputation system is accurate, then we get all the nice advantages that we can harvest from the reputation that I mentioned before. And it doesn't matter whether the secondary blockchain is good or bad. But if the reputation system is not accurate and the secondary blockchain is good, then there we're going to observe potential forks or stalling, and we can also potentially resolve it. So with that, I conclude my talk. Thank you.
Great, thank you very much. Let me just check if we have any questions. There doesn't seem to be any on Zulit. So I guess I was wondering, while you were giving that talk, is this open to any sort of denial of service type of attack, or?
I mean, all blockchains are, but the main point of this thing. So first of all, you can blend this thing with VRF-based, like private lottery mechanisms. But the second thing is that the reputation of a party is adjusted depending on how it behaves. And this means that parties with high reputation are expected to safeguard their network. If they don't, then the reputation gets lowered. So parties that have frequent denial of service attacks will actually eventually drop out of the set that is frequently selected in the next block selection.
Cool. Yeah, so there doesn't seem to be any questions on Zoom. So should we go to the next talk?
Yeah, yes, Clément, you can.
Hello.
Hello.
Do you hear me?
Yes, we can hear you.
Great. So share screen. Okay. Can you see my screen? Great.
I can see the screen, yes.
So hi everyone, thanks for being here for the presentation of the article. We worked with Thomas Ricosset from Thales and Pierre Meo from l'Université Catholique de Louvain. Our article is an implementation of a trancyphering using the homomorphic scheme TFHE and the symmetric stream cipher Philip. So first question, what is trancyphering? Trancyphering is a protocol that allows to bypass some of the issues of homomorphic encryption. Indeed, issue with homomorphic encryption is that it is bulky ciphertext waits a lot, and computation, encryption, decryption takes a lot of time. So you don't want to do these computations client side. What transciphering allows is from the client just to use a symmetric light encryption scheme. The client will then send this light cipher to the server, and the server will perform transciphering, which means transform the symmetric ciphertext into an homomorphic one. So how does this work? The idea is basically to homomorphically evaluate the decryption algorithm for the symmetric scheme. In order to do that, the server needs to have received previously an homomorphic cipher of the symmetric key. So the homomorphic scheme we used is TFHE, which was introduced in AsiaCrypt 2016. We didn't directly use the scheme as intended. Instead, we used a leveled homomorphic scheme we built with tools from the TFHE C library, which is public. And the stream cipher we used is Philip. So let's see how Philip works quickly. Basically, there is a key register, which is your symmetric key, and a public PRNG. Everything is public, the seed is public. The secret is only with the key. You start by doing operation with the key, like taking a subset and shuffling it, but basically just shuffling the key. These operations are easy to evaluate homomorphically. Besides, they don't take time, they don't add noise, they aren't real homomorphic operation. And then you end up with a state that goes through a filter. A filter is a Boolean function, and it needs to be properly chosen because the security of your stream cipher rely on the choice of this function. So we considered two families of filter, DSM filters. They are basically sum and product. So they are easy to homomorphically evaluate since we have an homomorphic addition and an homomorphic multiplication. And XOR mash filters, which are the sum of a XOR function and a majority function. They are a bit trickier to evaluate because majority function can be seen as product and sum easily. Basically, we used mux gates and how to say decisional circuit to evaluate this function homomorphically. We ended up with the following results. So the data that are presented as a key size of the symmetric key server side. So as I said earlier, you need an homomorphic encryption of the symmetric key. So this is the key we are talking about. And the latency. Latency is the time needed to output the first homomorphic bit. In the case of Philip, since it's a stream cipher, we send the bits one by one. Therefore, the latency is the same as the throughput, which means basically that we can perform a transciphering every 2 seconds, approximately, depending on the filter. We compared these results with other implementation of Philip. So the first line is the one presented in the first table. The second one is another scheme that we designed that is a bit special because you end up with an homomorphic cipher that you can't use to perform every homomorphic operation. However, you can bootstrap him and then use the classic TFHE scheme and perform fully homomorphic operation. So the time is lower, but you have to add extra operations that we didn't implement. So the TFHE scheme is just TFHE as intended with gate bootstrapping. So it's slower. And the last one is Philip with a second generation homomorphic scheme. We also compared the results with other transciphering schemes. We ended up with a good latency. However, most of them have a better throughput because they batch their messages, which means at the end they end up with homomorphic cipher, which contains thousands of messages. One improvement we could bring to our work is to do the same. And instead of encrypting binary messages, we could encrypt polynomials. And in our homomorphic cipher, we will therefore have 1,000 messages, and our throughput will be 1,000 times better. Thank you. Do you have any questions about the article?
Thank you for the talk, Clément. So, so I was wondering, you had this filter function, which is just which is just linear. Is it still fine to use a linear filter function for the cipher? What's the intuition why it works?
Yeah, so I haven't worked on the security of the symmetric scheme. However, it has been well studied in the past few years. It isn't the first time this scheme is used. It was designed by one of the co-authors of the article. And what I understood is that for the filter to be secure, you have its output need to be balanced, which means that it outputs the same number of 1 and 0, whatever. If you take all the entries, the output is balanced, and any sub-function of the filter need to be balanced, which means if you say, like, for example, the first variable is set to 0 or to 1, the resulting function, which has one less variable, has also a balanced output and etc. The security of Philippe is described in the article, which is referenced here, I think, but it was not the study we made with this article.
Right. Yeah, it seems a really nice homomorphically friendly cipher.
Yeah, it was built for it.
Yeah, cool. Yeah, I didn't see any questions on Zoom. Maybe let's move to the next talk, but there will probably be some time in the end. So if you have any questions, any of the speakers in the session.
If you have any question, you can ask me or send me an email or whatever. I'll answer them. Thank you very much.
Yeah, thank you.
Yeah, great. So this brings us to the last talk by Krzysztof Piaczek on delayed authentication, preventing replay and relay attacks in private contact tracing.
Okay, welcome. My name is Krzysztof Piaczek, and I'm from the Institute of Science and Technology, Austria, and I will tell you a little bit about digital contact tracing, and there will be an invited talk on Wednesday on that topic too, so you might be interested in that. Okay, so what is contact tracing? This is simply a term from public health, and it refers to the idea that one identifies contacts of diagnosed people to curb the distribution or the spread of contagious disease. And of course, it's a big topic now. And traditionally, this has been done by interviewing diagnosed people and asking them about their contacts. More recently, one tries to leverage the fact that all of us run around with mobile phones and somehow use these to help this contact tracing. And you've probably heard a lot of discussions about these because it was also popular in the news and the public media. And typically those discussions evolve around the efficiency of those schemes, that the privacy is very important. And one aspect that I think has not gotten the attention it needs, and I want to talk about today, is the security of those schemes. In particular, I will talk about the feasibility of launching large-scale false positives with those apps due to so-called replay and relay attacks, and how to prevent them. But before I do that, let me very shortly summarize, give a 1-minute summary of the Google Apple API, which is basically the scheme that underlies most of the deployed schemes those days. It's an extremely simple scheme, and it works as follows. So when you install the app, what the app does is it has a daily key. I hope you can see my mouse. So it has a daily key. From this key, every few minutes, every 10 minutes, a new identifier is derived deterministically, and that identifier is then just broadcast. At the same time, the app constantly records all the apps that it receives, and every app does both of those operations, receiving and sending. And should the party get diagnosed, so Kermit here gets diagnosed, then he gets the like a token that allows him to upload his keys of the last 2 weeks, say, to a server. Once a day, everyone downloads the keys that have been uploaded, and they check if what they have locally stored is consistent with one of the uploaded keys. And if yes, they kind of are alerted that they were in proximity of an infected person. So what can go wrong with this very simple protocol? So here is a very obvious attack. So let's say we have this adversary, a cookie monster, who simply collects lots of those beacons or identifiers that he sees, maybe at the hospital where he can expect somebody to get diagnosed soon. And then he replays all these beacons, maybe with the big antenna, so he doesn't have to run around, at the location that he wants to get shut down. And then later, if any one of those, let's say Kermit gets now diagnosed, he uploads his key, and Gonzo here will think he was in proximity with an infected person, even though this is far from the truth. He just was he received the beacon that was replayed to him. Relays attacks are similar, and I will not talk about them here. So basically what we do in this work is we show how to harden the existing protocols against replay and relay attacks. Now, this is not, this is a trivial problem. This is like a Crypto 101 problem. The point is we want to do this basically with our hands tied behind our back. So in particular, we want to achieve this without giving up any of the nice privacy properties this protocol has, without increasing the round complexity. So I just want the app to broadcast one beacon, just using super basic primitives, basically just symmetric crypto, maybe hashing, maybe IS if you want. And what's also going to be important is I want to keep the communication complexity. So I really just want to have a broadcast of 128 bits, which is important. All these things are important if one wants to use this solution as a, say, drop-in replacement for the Google Apple API as it is now. So in the last 2 or 3 minutes, I will actually show you the protocol, but let's start with the original protocol. That's a toy version of it. A very simple solution proposed by Baudonnet is to use a challenge response protocol. So the receiver, after getting the idea, will send a challenge and receive a tag, which is the message authentication code of the tag and the challenge. And later, when Kermit gets diagnosed, so Miss Piggy here will also verify that, and she learns the key, she will also verify the tag. It's not hard to see that this prevents replay attacks. Of course, it increases the round complexity, which is not a thing for these apps. Because they use this low energy Bluetooth, it's really a problem. A simple idea to fix that is to replace the challenge with the current time, and otherwise everything stays the same. Also, this prevents replay attacks at the later time point. Say the time is up to granularity of a second, so you cannot replay a message a second later. The problem is privacy. Now, the data that the sender and the receiver must jointly store locally on their phones reveals not only the minimal fact that they met at some point, but also at what time. And we don't want that. This is basically actually what the Google Apple API is doing, only that, so this is the daily key, so this identifiers are derived in some way from them, and some time-dependent value is added in this process, and roughly this value only changes every 10 minutes, which means privacy-wise, I can still figure out up to 10 minutes when 2 people met, if I get their phones, while replay attacks are still possible in the 10-minute window. So it seems to be a very unfortunate compromise that they did. So the question is, can we get kind of a privacy-preserving scheme which still prevents those attacks? And here is the solution we propose. It's called delayed authentication for reasons that will become clear in a second. So this is the protocol from before that is not privacy-preserving because it kind of uses the time. Now, the idea is to simply not authenticate the time, but instead authenticate the statistically binding commitment of the time. So the sender will pick some randomness, compute the commitment of the time, and then authenticate that. He will send over the randomness of the commitment. The receiver will recompute the commitment and just store the commitment. Not hard to see that this also is secure against replay attacks if the underlying building blocks are secure. And as importantly, it also is privacy preserving in the sense that now all the information stored jointly by Kermit and Miss Piggy are actually statistically independent of the time when they met, always assuming that they delete the time and everything, all the data that they don't actually use. Okay, that's all I have to say. Okay, so if you look in the paper, so this was a kind of an ad hoc protocol. In the paper, we actually abstract the more concrete symmetric primitive out of it called delayed message authentication code. It's defined like a regular message authentication code, except that verification has now 2 steps. The first step doesn't use the secret key at all, and the second, and it outputs a value that is statistically independent of the authenticated message, while the second step only takes this value that is independent of the message and the key. And there is a simple construction using a standard MAC and the commitment scheme. Okay, so this is the second last slide. I promised you that another important fact is, can we actually fit this into these 128 bits that are available in the Google Apple API? Because I said it uses this low energy Bluetooth. In total, there are 31 bits. 15 of them are already bound for all kinds of other data. So there are 16 bytes, 128 bits for this particular tag. And in the paper, I actually argued that maybe somewhat surprisingly, it's possible to actually fit all this data into this 128-bit tags with strong cryptographic security. It uses observations like the fact that I don't actually need really a commitment scheme, but only kind of a Vico notion, which I can get like randomness of 80 bits and still achieve 80 bits of computational security, things like that. Okay, that's it. Thank you for your attention. Just maybe two conclusions, so takeaway conclusions. I think what I showed you is that time can be used to prevent these replace attacks without giving anything up in terms of privacy, or almost nothing in terms of privacy or efficiency. In the paper, I also discussed relay attacks. There, you don't authenticate the time, but some coarse location-dependent data, cell tower ID, or coarse GPS coordinates, and you can also prevent these so-called relay attacks. And maybe a final question, the use of commitments in this scheme is very unintuitive. So usually for cryptographers, we use a commitment to commit to a message and later open it. Here, we actually commit to a message that everyone is supposed to know, so that later we can forget it and still authenticate it when the key becomes available later. So the question is this idea may be useful for other privacy preserving tools or mechanisms and so on? Thank you.
Great, thanks very much for that. That was really interesting. Let me just see if we have any more questions on Zulip. No, I can't see any. Yeah, so this technique is really specific to what Google and Apple devised. I see. What do you think about the other sort of the other techniques that were proposed for this contact tracing globally? I guess there was some.
Yeah, so I mean, exactly. There are lots of schemes. Maybe the most important discussion that is going on is between so-called centralized or decentralized. Basically, there is this other proposals that are, I think, used in France and maybe 1 or 2 other countries, where you do not upload the sender does not upload his key, but instead let's see. But instead, kind of the server has to know the identity of the persons and kind of will alert them if a person has been diagnosed. Those schemes are less suspicious, have less of a problem with replay attacks. They still have them, but to a lesser extent, because the server can see, if you try to do a really large-scale replay attack, and that's what we're worried about. I can always steal your phone and go somewhere and broadcast your token, but for these large-scale things, you could potentially see that already at the server level. So it's still an issue, but less of an issue. And I don't want to go into the discussion if decentralized or centralized is better. They both have trade-offs. I think Bodene's paper discusses them very nicely. So one important thing is, we will hear about it on Wednesday, maybe, that the centralized have the advantage that you get epidemiologist data, right? You can see potentially who got infected and use from that where are the hotspots and so on, and that might be additional usage other than just alerting that they were in proximity.
Great. Yeah, so if you don't have any other questions or comments, I guess we can finish. And thank everyone, thank all the speakers today. And yeah, I think that's it for today. So I guess we'll see everyone tomorrow.
Yeah, that's right, at 11 a.m. India time and 5:30 UTC.
Great.
Yeah. So thank you, James and Chris, for chairing this session. Thanks. Bye.
Thank you. Thank you all. Bye-bye.
Thank you.
See you tomorrow.